Balancing redox reactions. So when you have redox reactions, it's important not only to balance the amount of elements that you have on both sides, but also the amount of electrons. And then going around solving the problem using the correct mole ratios. A 0.376 gram sample of iron ore is dissolved in acid to reduce the iron to Fe2+. This acidic solution of iron 2+ is then titrated with 41.25 milliliters of 0.02140 molar potassium permanganate. Determine the mass percent of iron in the iron ore. The redox reaction for this titration is shown here. This is an unbalanced in acidic conditions. So just looking at it, you can already see that the charges are not balanced, and you can see that you have an oxygen here, but no oxygen on the other side. So before even going around trying to calculate and solve for the mass of iron, you would want to first balance your equation. The way to do that is to separate equation into two half reactions. So the iron's together and the permanganates together, and manganese. So therefore we have Fe2+ and Fe3+ and MnO4- and Mn2+. Then you want to balance the elements of both half reactions. So Fe2+ going to Fe3+ has 2 iron, so there's no need to balance that. And then MnO4- and Mn2+, the manganeses are both balanced because there's one of each. However, there's 4 oxygens on the left side and no oxygens on the right. Since this is an acidic solution, you add water to balance out the oxygens. So, since I have 4 oxygens, I'm going to add 4 waters. Now, I have 4 oxygens, 2 permanganates, but now I created this issue here. Then, on the other side, I will have to add the amount of hydrogen ions to balance all the elements. So 4 times 2 is 8, so I will need to add 8 hydrogen ions to the other side to completely balance out the reaction. Since it's a specific and acidic solution, this is how you can add the water. The water needed to be added because this is not a balanced reaction when there's oxygens on one side and not on the other. So you add your waters, and then you have to balance out your hydrogen ions. So now you've balanced out your elements, you have to balance out your charges. By adding the electrons. In order to do this, you have to determine what is being oxidized and what is being reduced. So if you write your 2 reactions down here, iron 2+, iron 3+, and then MnO4- plus 8 hydrogen ions makes +2 and 4 waters. So you're looking at your iron and your manganese. Okay, so iron went from 2 to 3. It increased in oxidation number. It became more positive, so it lost 1 electron. So you would add 1 electron to the product side. Then manganese Well, I know that I have oxygen is -2, and I have 4 oxygen, so that's -8. And it has to equal a total of -1. So in order to subtract 8 from something to get -1, manganese has to be +7, and this manganese is +2. So manganese went from +7 to +2. It went down in oxidation number, so it gained negativity, meaning it gained electrons. 7 to 2, the difference is 5, so it gained 5 electrons. And then, since it's being gained, that would go on the reactant side. So now you have your charges balanced, the elements balanced. Now you can sum up the equations. Sum up both half reactions and cancel out electrons. So you'll see what I mean by that. So if we just clean this up and rewrite, we have iron 2 plus makes iron 3 plus an electron. And then we have the 5 electrons plus MnO4 minus plus 8H plus makes Mn2 plus and 4 H2Os. So if you wanted to balance this, you would still be left with electrons. So multiply both sides equations to cancel out electrons in final. Because we don't show the electrons in the final reaction, and we already balanced them. So the second equation has 5 electrons. The first only has 1. So we can cancel out 5 electrons by multiplying the top by 5, therefore getting 5 iron 2 plus, 5 iron 3 plus, and 5 electrons. This will then cancel out my electrons, and I'd be left with my final reaction. 5 Fe2 plus MnO4 minus, and now I'd write my states, plus 8H plus makes 5 iron 3 plus Mn2 plus 4 H2O. And now you have your balanced reaction. So now you can go back and you can solve for the amount of iron that you want. So let's just get a little bit organized here. I have 41.25 milliliters of 0.02140 molar KMNO3. So KMNO4. KMNO4 splits up into K plus and MnO4 minus. Since it's a 1-to-1 ratio, we can assume that the 41.25 milliliters with that molarity is also for just the ionic form. So I'm going to write 41.25 milliliters here and 0.02140 molar here. My total mass is 0.376 grams. I want to know percent iron 2 plus. So I'm going to use my mole ratio to solve for the iron 2 plus using the equations that I just balanced. So I take my 41.25 milliliters, make it into liters since molarity is in liters, multiply it by the molarity to get moles of MnO4 minus. Then I use my mole ratio. I have 5 moles of iron 2 plus over 1 mole of MnO4 minus. And since I want mass, I have one more step and use the molar mass of iron. And then I just calculate that all together. 41.25 divided by 1,000 times the molarity, 214 times 5 times 55.85. And that gives me 0.2 0.247 grams, and that's not my answer yet since I want a percentage, then the percent iron becomes 0.247 grams divided by the total, 0.376 grams times 100, and that is equal to 65.56. I want 3 significant figures, so 65.6% iron. And then that's it. So just like a regular mole to mole conversion, using what we know about molarity and being able to use the volume to get moles, and then just stoichiometry, finding what you want, molar mass to get the grams, and then just back to the definition of percent mass, using the mass of the element that you want over the total times 100. The newer part in this was to make sure that your equation that you're using for the mole ratio is correctly balanced. So since this was a redox reaction, immediately you have to already use electrons to balance out your reactions. In a redox, you have something that's being oxidized and something that's being reduced. You separate the equation into 2 half reactions. Then, not only did you have to balance out the electrons, the charges, you also had to balance out your elements. The first one, for iron, we did not need to do anything but make sure that we balanced out the charge using the electron that was lost. For the second one, since we had oxygen on the left side but not the right, since it's told to be an acidic solution, we add water and hydrogen ion to balance out other elements, then balance out the charge. However, then you want to go back and sum up both reactions, and you have to get rid of your electrons. So you would multiply the equations. We only had to do one. Sometimes you have to do both to balance out the amount of electrons so that your electrons cancel and you're left with the exact correct balanced out equation with the charge balanced and the elements balanced.